I'm very happy to be here because it's great to see a room full of people who are interested in formula verification. You don't see that often. Quick show of hands. How many of you are computer scientists? Not sure. Uh, okay, so more than 50% is a good number. This talk will have a lot of examples. If you don't take away anything more than how we do the proofs or whatever, observe that there are certain problems in other areas of computer science where formal verification is needed. And why without formal verification, we can easily make mistakes in this, right? So that's sort of the line of what I'm going to talk about. This is joint work with Pranav, who's here, and Vimala, my PhD student who just graduated, and Karthik. Karthik did his PhD from IIC. So he's now a faculty at IIT Madras. So the setting for this talk is should be very familiar to you, right? So the setting is we've all used some sort of collaborative applications. We've used Google Docs. Some of you may have used Airtable or Figma for design, Overleaf for writing papers. And the idea of these collaborative applications is that there are multiple users who are collaborating on this application. They're all connected over the internet somehow, right? So we don't care where they are. You have some shared notion of state. And the problem is, given that you're connected over the internet is prone to disconnection. You can have network partitions which disconnect part of the users from other parts, or you may lose internet where you cannot access the app anymore. Right? We sort of understand this from ground up. And in fact, Google Docs has this offline mode. If you enable offline mode, it will still allow you to edit the document. When the connection restores, you can sort of connect to it and restore all of your edits. But the problem is these sort of offline editing is often retrofitted on top of a centralized application. Whenever you and I collaborate on Google Docs, all of our updates go to Google and the conflicts are resolved at the Google site. So the point here is I have multiple Google accounts on my machine and I enabled the offline editing on one of those accounts. And I was trying to edit a doc on a different account. And it said you cannot edit offline because offline sync is enabled for another user. So this is unfortunate, right? Google Docs is supposed to give you collaborative access, right? And today, Google Docs is the de facto way of any form of collaboration. And it is unfortunate that we have to have internet in order to collaborate. I have my machine. My machine is very powerful. I still want to edit my doc, but it is unfortunate that we have to have a live internet connection for editing my local document. So the world that we want to imagine is even in a disconnected setting or even in a connected setting, I choose to have my own versions of the doc. So you and I work on our own versions of the document, right? There could be multiple versions. Each of us edit those versions. And when the connection is restored or when I choose to share my updates, we sort of want to take all of these disjoint versions, combine them somehow, and then get a consistent version. So that's the goal. And the notion of consistency here is sort of defined per application, right? There's no universal version of what a consistent document, Google document is, or what a consistent notion of overleaf paper is. This is all domain specific, right? But the key is we all want to work locally. And then when we choose, we want to take our local updates, merge it somehow, right? That's a grand sort of vision for this. Internet was originally designed as a complete distributed system, right? Each one sort of works on their own thing and we use communication only. I mean, if you want to communicate, you go over this network. But if you look at the current status today, everything is online, right? You have to have internet to do your local edits to your document. So this is also known as local first software. We want to build software which is on your machine, local first, built for you to edit software on your machine locally. And then you want to collaborate, that has to be an operation that is fundamentally built from scratch, right? Somehow you know how to share it in a consistent way. So the question that we have been exploring for a couple of years is how do we build such applications? Our take on this is to embed the notion of replication itself into the data type design. So we'll see all about what they are. But by data types, what I mean is your basic notions of sets and counters and maps and whatnot. Some of you computer scientists may have taken data structures courses. We want to imagine such data structures to be designed from ground up for being able to have multiple copies of it. And locally, you can do some operations and then take that copies and somehow merge them together. That's the idea here. Everyone with me so far? Okay. So replicated data type are these kind of data types which allow you to sort of replicate it across multiple places and find the consistent merge. We work on this particular kind of replicated data type called the mergeable replicated data type. Some of you may have heard of CRDTs. Who's heard of convergent? Yeah, CRDTs are another form of giving similar idea. So convergent replicated data types also gives you this ability where you define data types and you can sort of put them together to get consistent semantics. We work on a different system model. Essentially, MRDTs are your sequential data types, your data types that you like and love, that you implement, that you program with locally, like stacks and queues. And you provide this extra thing called a three-way merge function. A three-way merge function is very much like Git. Who's used Git? You're all using MRDTs to some extent, right? I mean, you don't know it, but you're using it. So whenever you have a local edit in a branch and you say, oh, I want to merge it with someone else who has their own edit, what happens in Git is you take those two versions, two files typically, and then you merge it with this common ancestor, the version at which two of you diverged. So that gives you the causal context, the version at which you do two versions diverge and the two versions that you're trying to merge. And what you end up doing is to compute somehow how the final version should be. So in a typical document, if you edit one part, I edit another part, the merge is simple. The question is what happens when we edit the same thing, right? It says, I'm not going to help you. You fix the conflict, right? You tell me how to fix it. But the idea here is we are going to design data types such that the merge is a totem function, right? So the merge is always defined, right? So what that allows us to do is to be able to diverge and always come to a consistent merge. So here is a little example. We always start with counters because you can get all sort of complications just with the increment on the counter. Why would you want to care about counters? If you say implement something like your Twitter or Instagram, you have likes, you want to count likes. You don't want to have a single like counter in Instagram server where all of your likes go there, right? Really what you want to do is to locally accumulate the likes and sort of sum it up as an event. So suppose I have a replicated counter. So the keyword replica here means that it's one copy, right? That could be multiple replicas. I'm assuming there is a single replica whose value is 7. Just like Git, I can copy the state of this replica. I can fork it to have another counter, which is a copy of that, right? And this fork edge sort of captures the causal dependence. It's the history of how this counter came about. Each replica may be running on like a single machine or across the world. Doesn't matter. They don't need connections, just like Git, right? Git allows you to work locally without internet. Same idea. I can increment two versions to get 8 on one version and 10 on another version. And now, at a later point, I can choose to merge the two replicas. Right? Now, the question here is, what should be the merge? And here is where the smarts come in, right? So a sequential addition is just an addition. But when you want to merge, you have the two versions V1 and V2. So those are the two copies of the counters right now. And you have a lowest common ancestor. That's the causal ancestor that is common between the two divergent versions. What should be the result? Intuitively, right? Given that I started with 7, somebody did +1, they got 8. Some other person did +3, they got 10. What should be the result? Any 11, right? Why is it 11? You can now describe it as a three-way merge function, which says I have the lowest common ancestor version, right? That's here. And the difference between the current version and the lowest common ancestor. And that gives us 1 here. And similarly, the other version and the lowest common ancestor, that gives us 3. So if you sum it up, you basically get the idea of the common value and the two deltas, right? Which you sum it up and you get 11. This looks correct. This seems to work. But why is this correct? It intuitively makes sense. But why is this correct in the general sense? Right. That's the one. Right. And you have this particular. I mean, this looks intuitively makes sense. But why is it correct? So there is some notion of operations that are being applied, right? If you take the lowest common ancestor version and you apply these changes and you sort of sequentialize it, you will get to 11, right? That's the intuitive meaning that we have. But what we want to do is to sort of describe this function as this and potentially nothing else, right? I just want to describe it. And I want an automatic proof that this is correct. Firstly, for proving something to be correct, we need specifications, as Siddhartha and others have said. First, we need to agree on what the specification is, what a good specification is for these sort of executions. And secondly, how do we actually go ahead and prove it, right? That's the open challenge here. Yeah, everyone sees what we're trying to do. So think about these states, right? Think about these states. So variables and all of that is gone, right? These are the states. Somehow we know how to name those states.
Perfect simple scope, but now how is it LCA is like it stays common across different party. It sounds like a recipe and implement problem that you need to have like everyone be of the same.
A really good question. It's not an agreement problem. It's basically causal consistency, right? You have some initial state and everything evolves from there. So you don't need to agree. It's there in the history. It's there in the positive history. When I am at V2, right? If you follow these edges back, you get to the LC. Think about how Git merge works. I pull some branch from someone, I get their commit, right? But I also bring in all of their history. And we have a shared history from which we pull.
Okay, so there's like a online the central entity holding it. So
There's no central entity. Everything is completely distributed. Just think about Git. Git, we use GitHub, we think it is centralized, but Git is actually a completely distributed system, right? It's called a distributed version control system. As long as you have the entire commit history and we sort of port from the same version, if I bring all of your commits in, I will be able to find the LC. I'm just traversing a graph backwards. It's a directed acyclic graph. So you just follow it backwards to find the LC.
what is increments like are these scaffolded increments? Because what if we have like an initial statement, there are copies, and then there are two increments to the right copy, one increment to the left copy. But at the end, we have the same increment to both left and right copies. So how are these increments like differentiated in these cases?
You don't actually differentiate instance at all. You just look at the state. You got to care about how it came about. You care about what directness of that.
In this case, now we have an increment that goes of the state shared. So if we apply LCA plus V1 minus LCA,
so
V2 minus LCA, then that will give.
Good question, right? So let's say I want to merge V1 and this state, right? What would be the result? What should be the result of this merge? If I merge this state directly, it should be 8. Why is that? Because the algebra works out here, right? Because the difference here is 0. And the idea is that you have an LCA here, right? And the LCA sort of remembers where you forked off. So it doesn't matter if you merge here, you have sort of some increments here, some other increments here. The new LCA will be this, not the original one.
Be before the shared increment.
Sorry?
The merge step would be before the shared increment. It will also.
So the LCA will come down. You look at the lowest common ancestor, right? The previous LCA is gone. You sort of look at where the causal divergence happened. Yeah.
You basically in this case, if both the deltas to same, then you're basically just adding in it. State.
Yeah. So that's the key, right? And why does this all work is what you're getting to, right? Why should it work is what we are going to see. Yeah.
So that function to work, we must have decoupled the increment value from the original state. So for example, when you prepare a gate, you can't really apply a change without an existence of an exact state.
So we have the entire state. So the assumption here is I have 7. I can do some local operations. It can be anything at all, right? I want to get to some other state.
Yeah, but the must be dependent on whether the value was self.
Doesn't matter. So so that's where the semantics come in. I'm implementing an increment only counter here. You could do a different counter, which says increment and decrement. Okay.
Say you wouldn't increment if the value weren't sub.
That's okay. And you don't change the state at that point.
Yes, then the merging wouldn't work because you already done a +1 here.
Doesn't matter. That's an independent increment. all you care about is what's the final state. I chose to increment, you didn't choose to increment. So there is no obligation that you have to do an increment here. It just happened to be some operation that you did.
What I'm trying to say is that the sequencing that you discussed would be violated
You
such a condition were to be.
So this is if you choose not to increment, this +3 wouldn't even occur. It's not like this +3 is sort of, if you see 7 and you say, oh, if it is 7, I'm not going to increment, then you wouldn't even change the state. Okay,
So say you wouldn't increment P sigma 8.
fine.
So if you were to sequence the +3 after +1, the +3 would have never occurred.
Then nobody claims that for all possible intents and all possible function, this operation works.
So we are specifically thinking about a logic where you can do local increments, right? And that's where this intent comes in, right? So the idea here is we are not implementing your counter where it is supposed to be like, if it ever comes to 8, I'm not going to increment. You only do the operations based on your local state. So we are post facto reconciling this behavior. You are absolutely right. This is not a general purpose scheme where if you add a condition which says, if I see 8, I won't increment, then you won't be able to reconcile this linearization. We can't prove that in this framework.
So we are kind of assuming that all the increments are somewhat independent from each other.
They are independent. They
So
are
if I have
completely
two forks and I'm incrementing them based on seconds elapsed on the system clock, then you can't just
so
include it.
you have to somehow post facto give a rationalization, right? So this is a really good question. We'll sort of come back to that later, right? So we'll see how to merge this. Okay, so let me proceed. So I'll give you one more example. This is a set, right? Set as in a set where you can add and remove, right? And if you think about it, if you and I share a set, you add an element, I remove the very same element, we have to decide whether to keep the element in the set or whether to remove it, right? So this is what is known as a conflict. So these are operations that conflict with each other. We can't concurrently add and remove the same element. And we have to now make a choice, a deterministic choice of whether to keep the element at the end or not have the element. So the choice that one version of the distributed set makes is add wins, right? So if we have a concurrent add and remove of the same element, the add will survive in the set. So the representation of this is a bit different. So you have the elements, but you associate a unique timestamp. Somehow the system gives you a timestamp, right? And every time you add an element, you pick this unique timestamp and add it to this set, right? So initially my set has A and B and the timestamps are 1 and 2. Doesn't matter what the timestamps are. Timestamps are internal to the representation. So when you add an element, you pick a fresh timestamp and then you add it, right? So you had A, 1, now you have A, 3 as well. And then you can concurrently remove the same element. You can now say A is gone. There, what you do is, because you can have duplicate elements, same element but with different timestamps, you have to walk through this, fold through this entire list when you want to say remove every copy of A from the list. So all of that is gone. So there was only one copy there. So this other side removed A, you have B, 2. Now what should be the merge? Intuitively, what should be the merge? Given that we are thinking about add win set. So these are, whenever I draw these as diagrams where they are concurrent. So remove and add are concurrent.
Then it will be the right man, sorry. And please.
Add wins, right? So let's ask a different question. So should A be in the set?
Yeah, keep it on.
Should B be in the set? Yes, right? We haven't modified B at all. So B should also be in the set. So read just returns the set removing IDs, but the merge function here is this little thing. I mean, it's more complicated than the counter, but essentially it's trying to sort of capture the same idea.
But it was not added after.
Exactly. That's the idea. So essentially merge is taking the LCA version, the version 1 and 2, and it's taking the intersection of all 3, right? So element which hasn't changed, B, is there in the set, right? I'll come after finishing this. If you had removed an element, right, that won't be in the intersection of all 3. So deleted elements are gone. Now you have to make sure the final set captures the added elements. So you take the difference, set difference between the version and the LCA on both sides, and you union that to this intersection. This seems intuitively right. Why is that correct?
Just first removed A and then added A.
Yeah.
Then wouldn't you end up with the same since with 3 is by right in the market, right?
That's exactly what we are going to later. That's the observation. So essentially, what you are sort of doing is you are forced rationalizing what the linearization should be. Right. Okay. I see this. One way I can think about a linear order is do a remove first and then the add. That's what you're saying, right?
Yeah, like you can multiple ways which way enter the B2 eighth.
But that is certainly one way. When you're not concurrent remove and add, you sort of linearize that as add, remove first, and then the add. Yeah, so that's exactly the observation. Okay, so let's look at the admin's strategy. Yeah, that's because of the admin strategy. You can also do remove wins and leave that as an exercise, right? Sorry. You can also do delete wins, remove wins. That's a different set that gives you ribbon semantics.
But I point, so a bit jumping a bit, because the final universal thing is it should be symmetric, and also if the threads are identical to each other, which you put some sort of identical hence.
Yeah, so it turns out that that's not alone enough.
Yeah, it won't be enough.
Yeah,
Those are things that are universal, which should be for no
that should
then they would be choices.
Yes, exactly. So question.
Like remove deletes all instances here.
So in this implementation, it has to remove all instances because all of these duplicates are basically capturing unique adds, right? When you do a remove, you just remove that element from the set. No. But the interface is going to be like, if you call remove on A, I'm going to remove all A's irrespective of timestamp. That's the implementation. Okay. So the point here is this implementation is inefficient. It's the space usage is the number of adds which are alike, right? If I keep adding element one after the other without checking whether the element was there, I'm going to keep adding new elements. Right? So now here is a different implementation. This is going to give you a more efficient one. It's a triple now. Every element is a triple. It has the element, the replica ID at which it was added, and a timestamp. Okay. So now the protocol is different. If you add an element at some replica R2, what you first have to do is you remove all triples which are that element added at that replica with whatever timestamp. So all the previous elements that you have added at this replica, you remove it. And then you add one a new triple with the new timestamp. Right. So
The replica IDs are like it has to be the partial order.
replica IDs are
What is the structure on them? Is it the partial order of being an ancestor or not?
no. That is replica IDs are just unique.
Yeah,
They don't even
strategy will use the fact that there's a partial order on them. It's right.
The underlying mechanism will actually sort it out. We don't actually. Yeah, we are not going to care about what that is. There was a question from that.
The replica ID is like if they are different, more than two people, they are ID of.
So they will be assuming they are unique. So typical standard node IDs, right? We just take them as unique, generate a very long UUID, right? And hope that the collision doesn't happen.
Previous one doesn't work for that because it doesn't have replica IDs.
It doesn't happen. It doesn't work there. I mean, this is an extension of that to reduce the space usage. Because we want to reduce the space usage. So earlier one had, when you add in,
Assuming you will end up removing.
No, this is not assuming you will end up removing. Actually, the original version and the new version both have A and B, right? But what I've done is I've recorded. So what are the elements here? A, B. But what I've recorded is I'm adding a new A, which is sort of superseding all A's that I've added on this replica.
This will be treating it more like a set rather than.
Yeah.
I was thinking more in terms of a list.
Yeah, we are treating it like a set, but we will still have duplicates because elements that are added by different replicas will be there. Yeah, so, and remove and merge remains the same. Now you can work it out, but as I said, the space usage now will be the number of live elements times n in the worst case, because every replica can add A, so you'll have n copies. Again, the question is, why is this correct, right? So you can keep on adding this. I'll skip this runtime support. Essentially, there's a Git-like mechanism that is down there. I mentioned that already. You can just follow along the path, right? So if I want to find the LCA between E and C, you just follow along. That's the lowest transistor. That is what you have. You can ask for LCA of E and B, and LCA is B here. The lowest common ancestor of E and B is just B. And this runtime system allows you to do garbage collection. So if there are two replicas which are just F and G, you don't care about the past history at all. It keeps around all history because you might want to access the previous version. Here you can garbage collect it, right? You just keep the lowest common ancestor, and anything above, you can keep throwing it away. So the point here is, this is all sort of well known. And in fact, a CRDT version of this was implemented, which had a space complexity close to this. And folks took this paper and implemented this in a database called React. React is this eventually consistent database, which implemented this particular data type, right? And it was buggy. It was buggy because they said implementing CRDTs can be quite challenging. State-based CRDT, you have to design them as lattices that are inflationary. Every operation has to move up the lattice, and your merge function has to be deterministic and compute the least upper bound in the lattice, right? So that's the way they've constructed it. They've gotten it wrong multiple times. In fact, it went to production, and then somebody observed that they removed an element and they kept adding it again. But the element is completely gone. Ran it. It was just gone to the black hole, right? And they discovered post facto how this was done, and this was fixed. This is not an isolated incident. This collaborative editing, right, which is completely distributed collaborative editing, it's like an open challenge that's been looked at for many, many years. Martin Kleppmann is one of those people. If you've done distributed systems, there is a very famous book, Designing Data-Intensive Applications. So he wrote that book. They published a paper, which again, they found a few years later that there were serious flaws in the paper. Definition was wrong, and it didn't even converge, right? So they fixed it later. But what we want to do is to be able to verify the correctness of replicated data types, right? And yeah, what's common between designing RDTs and pen and paper proofs? I make mistakes in both, right? So we've been looking at a bunch of techniques, machine check proofs using SMT solvers, proof-oriented programming languages, proof assistance, whatnot. The full gamut, right? So Ilya mentioned multimodal verification. We've been doing multimodal by jumping across tools. There are a series of papers around this, but I'll talk about just one of them, which is before that, you can't just prove convergence and call it sufficient, right? One way to sort of think about this is, look, this is a two-way merge function. There is no LCA. Given two versions, prove that it is commutative, idempotent, and associative. Is that sufficient for capturing the intent of the data type? You would quickly discover it's not. So take the same example. I want to come up with a function here. I want that function to satisfy this. Is that sufficient to satisfy the intent of what an increment-only counter is? Is there a unique inhabitant that will satisfy these three properties and capture the intent of what we are trying to do here? No, right? You can give many, many functions. I can give max function here, right? That is commutative, idempotent, and associative, but it would give us the wrong answer here, right? So just proving this algebraic properties alone is not sufficient, right? There is something else going on, which some of you alluded to, right?
So here I add a property that if the two branches are identical,
Yeah.
then the result should be equal to that of each branch. Oh, but max satisfies that also.
That also, right? So
Okay.
people have formalized this, but this is not sufficient because the intent is not being captured, right? And that's where this idea that you suggested, we may have a complicated execution graph, but think about mu's as merges and OPs as operations. Can we think about the final states, sigma 5 and 6, as some linearization, some sequence of operations that we apply on the initial state, sigma 0, so that they converge, right? They converge and they have to satisfy some goodness property. The goodness we think about is this linearization. Convergence is sigma 5 and 6, right? These two states, which I obtain by different sequence of merges, both are in fact the same state. So if you and I operate on a document, you merge my document and you merge my document here and then here. I merge your document at this point, right? both of us have the same document at the end. If you have different documents, then we pay. That's the convergence. Any other questions?
Some I start already, the sequential scheduling and all is database concurrency as well.
Yeah. So
Translate and down.
really, really good question. So database concurrency, serializability, they request coordination, right? Fundamentally there's a law, and everyone agrees that when someone works a law, no, he cannot edit the law. Here we don't have a law. We cannot have a law, right? Because you might hold a law and internet gets disconnected. I can't edit my code. That's what we expect. That's what we want to show, right? And one way to do that is to have a single linearization. Prove that there is a single linearization, or if you have multiple linearizations, all of them converge to the sweet thing. Right? Actually, this is just sort of meta theoretic, right? We are not actually going to think about operations at all. When you operate with Git, you just have the commits and the document state at that point. You don't remember I just a backspace here, I deleted that character, right? We just have that state. But we want to still post rationalize the final state based on the edits that we got. Same idea.
BFAs. Because this the structure is very similar to what the graph thing, which were local level rules from that thing, but just
There's a bunch of graph theoretic approaches here. We haven't looked at much of that. Some of these doesn't work. I can talk to you offline about it. I think I'm running short of time. I'll go a little bit over. Yeah, sure. I'll focus on the key bits. Replication aware linearizability is this idea that we didn't come up with. Some other people came up with that. The idea is that there is this notion of linearizability for concurrent objects. Some of you may have done studied concurrent systems. Essentially, this is similar to serializability, but for individual objects. I can execute concurrent methods in any order, but the final state that I observe is the same as these functions taking effect atomically at some point, right? And the execution is an interleaving of these atomic operations. So there's a single sequential linearization that can explain what the final state is. So there's a little bit of a modification to that to take care of replication. We are doing operations that are fundamentally do not involve a lock. So we have to post-rationalize some of these behaviors. So I will skip this. I will also skip this, but I will just give you what the definition is. Yeah, let's do this. What do we want, right? We want to describe our data types, right? We have this nice property, which is this linearizability, specifically replication aware linearizability. I want to be able to automatically prove that given a data type that holds. So what do I expect from the developer? I expect the implementation of the set, right? The three-way merge function and basic set operations, add and remove, how that should be done. And I also require this conflict resolution equation, which is what you had mentioned. So if you have a concurrent remove and add, how do you sort of rationalize their order? In an add win set, you would say that if you have remove of A and add of A, order them in the linear order such that remove appears before add. So this will ensure that if you had concurrent operations, you first remove and then you add it, so the element would separate out. This is just what we require, and we have a system which can verify this. I'll get to that eventually, but essentially this is what the developer would provide. They would say, oh, my state is set of elements and the timestamps, right? So it's a pair of element and the timestamp. It's a set of that. I have add and remove. Add simply adds the element. So we define updates as state transformers. It's all purely functional, right? So you take a state, sigma here. The system gives you a timestamp and a replica ID. What does add do? Add produces a new state where it's the old state with a comma t, the new element and the new timestamp added. Remove produces a new state where if you're removing A, you remove all the occurrences of A from the sigma. Yeah, and merge is the same as what we had seen before. RC relation is just what we saw in the previous execution. So let's take another example. So if you have initially A comma 1 and you remove A here, you get an empty set. You added A here. Let's say the timestamp is 2. You have A comma 1 and A comma 2 here. When you merge, you apply this operation, you will find that the final state is A comma 2. How can you reconcile this? You can sort of reconcile this as starting from the initial state, right? RC says how to order the a concurrent remove and add. So do remove and then add. So you first do the remove and then you do the add. You will end up with a command. Right? So this is telling you how to sort of linearize the updates. So I mentioned this linearization order where I just described what is the conflicting operations, but there are lots of operations that are happening. So what is the supposedly what is the possible linearization order? This definition gives you that. So given two events E1 and E2, I would have to linearize E1 before E2. According to this, what is that? If E1 is visible to E2 and E1 and E2 cannot be commuted, right? Then they have to be preserved in order. What does this mean? If I add and then remove the element, right? Remove sees that add. So you cannot commute there, right? But on the other hand, what it does allow you to do is if you do an add and then another add, you can commute there. Doesn't matter. Okay. The second part here says that for concurrent events, E1 and E2, you order them by this RC relation, right? So this is what we saw earlier, right? For concurrent events which are in RC relation, you order them by making sure that E1 occurs before E2. So that's what we have here, which is what we ended. There is a side condition here, unless there is absorber. Frankly, this sort of post rationalization of how to let this go through for practical purposes. But it turns out it has a good meaning, right? So essentially, if you look at these two, right, RC relation says that in the sequentialization, remove must occur before add. But if you had another remove here, it doesn't matter in which order you do these operations. You can remove and add or add and remove, but the final remove anyway sort of erases the effect of those operations, right? So what this allows you to do is to free up this ordering. This ordering obligation can be freed up. So you can end up with the linearization. So without this side condition, very well-defined execution may not be linearized at all. Anyway, so that's a linearization order. So we have a little theorem. So how does this all end up being proved? It's very hard to directly prove this RA linearizability. So this is quite complicated, right? So this equation that we see here is like it quantifies over all events, right? And you have to sort of prove it somehow. It's not even clear how you would go about proving this.
That's obvious that the human always exists.
It doesn't. It's not even obvious it exists, right? It might not exist for lots of data structures, right? But if it does exist, how do we sort of go about proving it? What we've done in this work is we've broken this down into 24 verification conditions, right? Essentially, these are little obligations that you have to prove. And we have meta theory which says that if you satisfy this 24, RA linearizability is, I mean, it's adequate to prove RA linearizability. And in fact, your data structure may be RA linearizable, but this approach may not give you the proof for that. It's simplification one way, right? Every RA linearizable data structure will not satisfy these 24 pieces. It's meant to be a practical one. And what we've done is we've automatically set it up in such a way that we can automatically discharge it through an SMT solver. So you implement it, you don't have any other obligation. SMT solver would discharge all of them. Okay, so we verified many of these RDTs. You just write the code, right? There's no proof to be written. And this is quite magical. It works for lots of cases. And this is where the lead part comes in, right? So we did this in this language called the F star, which is a automated, it's a language like OCaml. It's a functional programming language, which is backed by a SMT solver. It's like Daphne, right? It's a little bit more powerful than Daphne in terms of the kind of programs it can represent, but it is also much less well engineered in terms of tooling than Daphne. SMT data proofs are quite terrible. If you just had an SMT, you implement a particular data type and you ask, okay, I am very sure this data type should satisfy the 24 VCs. Maybe you made a little bug somewhere, right? And an SMT can say yes or no, but it can also give up. It just says, I don't know, right? And you have no feedback. So I think many of the speakers have mentioned, right? So proof reconstruction is a challenging, you can have a SMT model, Z3 doesn't even give you a model back often, right? Which is what I understand.
Yeah.
And to sort of lift it back into F star to have a counterexample to say, hey, here is a particular execution that broke is impossible. Often what ends up happening is you write something which you hold is true, and the compiler just says no, right? And that's not a good development environment, right? It's great that we proved it, but it was not pleasant getting there. And the DCB includes the SMT solver. We use Z3. It's like thousands of lines of C++ code. And the worst part is SMT-aided proofs are very brittle. So every version of FSTAR is tied to a particular version of Z3. When you want to do these proofs, you have to give fuel and unfolding and all of these extra parameters that have no meaning with respect to what the program that you're writing is. You have to finely tune it. And if you upgrade Z3, all of your proofs are broken. This is like works on my machine, but at a terrible scale, right? So here is where we ported this framework to Lean. Pranav did most of the work here. Much smaller TCB, we can do proofs directly. We still use an SMT aided. We still use SMT for some of the proofs. Lean Blaster, we use Lean Blaster, which doesn't give us proof reconstruction. Which is the one that gives us proof reconstruction? Lean SMT gives you. So in cases where we can discharge the proofs using Lean SMT, we do it and we reconstruct the proof, right? Which means you no longer depend on the solver, right? We can also do wonderful property-based testing, counterexample generation, visualization, right? But what it has really opened up is agentic proof-oriented programming, right? Which is, I have these 24 verification conditions where I have a meta theory which shows that if you can prove this 24, my data structure is RA linearizable. So all I want to care about is I give you the implementation of the data structure. I let some agent go ahead and prove this 24 VCs. And if I can find proofs for that, then I'm done. I have this very nice property that it is RA linearizable. It's sort of giving you this guardrail, right? It's the guardrail that you have to satisfy in order to ensure that your implementation is RA linearizable. So in fact, moving to Lean was motivated by other reasons, but it turns out to be great for agentic proofs. So after some of the initial work was done, we've been looking at other papers which publish individual data structures, replicated data types. I take these papers, I point it at a plot and say, look, implement this in our system SAL. What you have to go through is tens of lines of code where you sort of see whether the operations make sense, right? Whether the RC relation makes sense. And the rest of it is done by just Lean, right? And we have a meta theory. So we know that if these VCs are proved, then we have RA linearizable. So one thing which is very interesting is this Peritext paper. It's a collaborative rich text editing where you can also do things like bold, italics. How do you do all of that? You can add URLs. What happens when somebody adds a URL, other person sort of holds part of the URL? What are the semantics? In fact, what the paper did is they have a bunch of algorithms and theorems where they say, here are the tests for intent preservation. So there are multiple tests where they say convergence holds, but also here is the semantics. Just to give you an idea, they will have tests like this, right? It says if Alice does bold of the fox and Bob does bold of a fox jump, the end result should be this. In fact, many collaborative rich text editors make mistakes here. So they have given us examples. In fact, what we end up doing is we turn these examples into proofs. So we point these examples and then we generalize them and ask Lee to sort of go ahead and prove it with Claude, right? And all you have to do is to ensure that the specifications are correct, which you can read the example and just get confidence. One last thing is once you prove it, some of the things that were very complicated become very easy. If you want to just extract an implementation, you can point agent at it and say, give me implementations of all the data structures that we have implemented. And you can go to this fplaunchpad.org/sal, where you can play around with many of the data structures that we have. Right? So it's quite fun because this is the interactive bit that we get promised, right? I want to build a collaborative text editor. I know how to do proofs. I have a proved version of it. Of course, this is not foundational. Nothing is proved here. It's like vibe coded, but vibe coded from the specifications, right? I have a correct implementation. I'm asking the agent to vibe code it. I mean, this does open up questions of how do you actually encode these apps? Maybe just do the proofs first and ask agents to vibe code it. That's the better way to build apps in the future. Anyway, so I'll stop here. I've taken a bunch of time. The development itself is in a GitHub repo, which I think you can get to from fplaunchpad.org/sal. It's a very big development. The obligation for the developer is they just implement something. You don't have to do any proofs. The system will automatically find the proofs for you and give you this nice property of linearization. That's the big take.
Agents which are building your bypassing these and everybody to come to the client business.
No. Any other questions? I'm happy to answer questions.
24 religious meditations. They are sufficient, but alternate necessary. Were they motivated by any like subclass of data types?
Yeah, so they were really good questions. They were specifically motivated by the MRDTs that we had already built, right? And what the induction procedure is interesting. I don't want to go through the details of it. Essentially, what you want to do is you reach a particular state, right? And you have a sequence of operations on the left-hand side and sequence of operations from the right-hand side. The induction procedure tries to peel one operation at a time and sort of tries to linearize it and go backwards, right? It's a bottom-up linearization. It was motivated by like the existing data structures that we had. But once we came up with that definition of LO with that additional condition, the existing ones we were able to prove. There are things that you can't prove, like the one that was mentioned here with the increment not being applied at 8. But for the ones that people care about in this area, we were able to prove all of them.
Question is, this is a lean proof. Does the 24 imply that the
I just finished the lean proof this morning.
So,
The meta theory was pen and paper.
oh, you had a meta theory, but
Yeah.
it's now formula.
It's now formalized.
So my question was going to be that if someone points GPT 5.5
Ah.
to the lean proof,
Yeah.
or maybe this, and ask, can you strengthen the result? Meaning weaken the 24, reduce it a lot, or so
Actually,
like that. And because you know lean proof and you've fixed your
Yeah.
final target,
Yeah.
you know whether you're correct or wrong.
In fact, this
I
is
would
what
be surprised if say 5.5 Pro can actually improve it.
No, this is in fact
Yeah.
what happened. So the kind of data structures that you said have preconditions, right? If I have 8, then I won't do the increment, right? This is specifically the kind of things that show up when you do collaborative editing. So one way to sort of think about collaborative editing is instead of thinking about your cursor as inserting at a given index, it inserts after a particular element. So you have to have a particular element and you say, now if the element is A, I add a B after A, right? But what if somebody else deleted A, right? So now you have to find a home for A somewhere else. So deletion doesn't apply in case, insert doesn't apply in case the original element was deleted. So this is like a precondition. So the new framework that I proved is an extension of it, completely done through Plot. I have a data structure. I know what the correctness condition is. I said, look, this has to work. Think about the correctness. You have to still prompt it to say, here's the shape of what you want. It has to have a precondition, right? It has to have some correctness notion of, it has to have an invariant on the state of the data structure, right? So if you think about this data structure, it has to be a connected tree, right? Some of these are internal invariants, but once you specify that, it derives a framework from it. It's surprising and it proved the meta theory.
But that invariant must be non-trivial because otherwise Git would have worked out of the box.
Git doesn't work out of the box because
Because of set precondition.
no, Git doesn't know how to handle anything other than text files.
But in bytes.
No, but I have a stream of bytes here. I have a stream of other bytes there. How do I know I can merge this? Right? I need semantics to sort of think about what the merge should be, right? You think about counters. Why should that 5 and 8 here be merged in a certain way? This is like a function that you have to provide. You can't really sort of extend what Git can do. It is fundamentally just knows about text files. And that is where the interesting things come in. And Git gives up when you have a conflict. Here, everything is about conflict. Yeah, it's not, multimodal is already overloaded, but we can overload it once more. But I think the right way to imagine this is it's Git, but for arbitrary data types, right? And the data type has to satisfy this three-way merge function. If you can give a three-way merge function, you will get a MRDT, but you won't get a RA linearizable MRDT, which is what the proof is. Okay. Question? No? Okay.
They're studying this for the class of or they get used but you in it. Is it an exact character you in those cases? Like, most of them?
Yeah. It goes both ways. Actually, we can't go the reverse direction, right? So given it is, we can't even, our whole definition of array linear, I can't even start with the proof of array linearizability. My proof actually depends on the 24 VCs. So it doesn't go both ways. I don't know how to prove array linearizability without using the VCs.
Okay, welcome back. I think everyone was eager for Ilya's second talk, or third if you count my already informal sessions. This one on distributed Wales, which is that's distributed verification.
Yeah.
Verification, absolute.
All right. Yeah. Thanks again. That's me. Hope you are not tired hearing me monologuing under a very judgmental stare of Ramanujan, who's right there. I'm gonna try to convince you that we want to verify distributed systems and LeanLang. Okay, so this has been here for a while. I'll let it be here for another minute or two. So there is another tool that we have built on top of Lean, actually using the Loom framework. That is also something that powers Velvet. And in fact, Veil is what started this our journey into Lean about 3 years ago, when it was before the AI craze, but Lean 4 just came out. We heard that it has good meta programming. And at that time, with my student George, we spent, well, basically his entire PhD and also like many years prior to that, me by myself, trying to crack a problem of building a good tool to prototype, validate, and verify distributed systems. So like if you open any paper on distributed systems that is published in the verification of programming languages conferences, they all start with the same sentence, modular, like some word permutations. Distributed systems are notoriously difficult to get right. So it's like a running joke now that you need to start a paper from this sentence. And the reason is that well, there's a lot of stuff happening in distributed systems. Their definitions are surprisingly small compared to, or at least the descriptions of their protocols are surprisingly small compared to other pieces of software that we care about. But because there is a lot of concurrency, there are a lot of asynchrony, there is a communication, there are possible faults. Obviously, the verification tends to get quite hairy. So I'm gonna go and give a little bit of a history walk of verifying distributed systems. So I presume by now you have either opened this LeanWeb form that runs a version of Whale, or you have cloned the repository and you build the branch, or it's okay if you haven't done any of that. So you just stay with me and there will be some live demo in the middle of this talk. Okay, so the title of the talk is Multimodal Verification of Distributed Systems in Lean. So multimodality is kind of the running theme of this series of tutorials that I'm giving here, and we'll see how it works in this context. And actually not just mine, so Casey just give a talk on multi-modal verification as well. All right, so we are going to talk about different domain-specific framework, which is also implemented as a library. And this is a framework specifically for verifying distributed protocols. So I don't know whether distributed programming is a part of the standard curriculum at your department university. It actually wasn't part of mine, so I learned about them much later in the grad school. So what are the distributed protocols? Well, they are certain class of algorithms. And they are the algorithms that solve effectively a multi-party agreement problem. So they define how multiple parties, typically referred to as nodes, you can think of them as copies of the same program that run in different machines or executed by different threads on the same machine. How can they collaborate with each other to achieve a common goal? And this has deep roots in human history because each human is like an individual node agent, if you want, if we want to be simplistic. And we often need to collaborate, believe it or not, to solve the problems. So this is something that attracted the attention of very prominent luminaries of computer science as early as in the 70s, long before the practical need in distributed system became a real thing. Nowadays, obviously, like we use distributed systems all the time without even realizing that. So this is the paper that usually is taught in the standard computer science classes on vector clocks, so time clocks and the ordering of events, distributed system by Leslie Lamport. So you know how it's a safe bet to say that maybe like half, if not more, of the useful things when it comes to distributed computing is invented by Leslie Lamport. So that's the same person who did LaTeX and TLA Plus, the tool that we will talk more about later. And he's still alive and well. He received the Turing Award for all the wonderful things that he has done in 2014, and he has recently retired from Microsoft Research. So this is one of the seminal papers, basically like how several nodes talking to each other can establish a common understanding of which things happened first at which of them. After that, there are lots of research on solving the problem of mutual exclusion. So imagine that we have a unique resource. So we have a database that many processes want to write into. So how do we design effectively lock-in protocols to do that? And everyone's favorite example, so what's called a transactional commit. So I didn't find a canonical reference on transactional commit problem, but this is the slide from Leslie Lamport's lectures on TLA+, where he says, well, if you want to think what is a multi-stage commit is, think of a wedding. So we have a bride, and we have a groom, and we have the minister. And before the final commitment happens, so the ministers ask both of them whether they agree to marry each other. And only if both of them say yes, then the commitment happens. And then if one of them says no, there should be no commitment. And more importantly, that should be the common understanding. So it shouldn't be the case that one of the, so either the groom or the bride like decided that the marriage has been concluded, and the other one has rejected it. And then I'm not going to show it, but like you are welcome to look for Leslie Lamport's video course on TLA+. It's probably will take 2 or 3 hours of your life. It's an amazing piece of material to watch, just to understand what it's like to reason about protocols. And then the next slide on this course says, let's think of a very progressive wedding. So we have multiple grooms and we have multiple brides, and they all want to marry. And that's like his analogy of distributed commit in the databases, which goes through the same 2 phases. Okay, so what makes distributed protocols even more interesting from the perspective of defining and proving their correctness is not only they need to do something useful, they need to do so while some of the nodes might fail. So this is something that like doesn't happen frequently in ordinary algorithms. So we basically consider our program either like executing to the conclusion or maybe throwing an exception, but it's not like some parts of the program succeeded, some parts of the program didn't. And in distributed systems, that happens all the time. This is actually something that surprisingly makes construction of these protocols much more complicated, because usually the reason is based on some sort of majority argument. So the success is declared when the majority of the nodes reached the common result. And the researchers started to look at it since late 1980s. So this is by Barbara Liskov and her students. That's the same Liskov as Liskov substitution principle. So she did a lot of seminal work in programming languages and then moved to distributed computing. Obviously, Lamport himself, that's probably one of the most cited and least read papers on the protocol called Paxos. Paxos is an island, a real island in Greece. And the way Lamport decided to introduce a protocol for reaching a consensus, an agreement in the presence of failures is through the fable about the parliament that was assembling on the Greek island of Paxos, where some of the members of the parliament could be late or they could not join, and they were exchanging messages by sending messengers, and the messengers were forgetful, so they were dropping messages, and the analogy goes on and on and on, and everyone likes to tell that this has a fable, but it obscures greatly the presentation of the algorithm. So Lamport himself on his webpage, he has like short anecdotes about pretty much every single paper he has written, and the anecdote about this one that he was pretty damn proud about the fable, and then it was one of the worst presentation ideas that he had in his career, because no one actually understood what is happening in the protocol. So he actually had to write a follow-up paper called Paxos Made Simple, which just explained the algorithm as an algorithm without any fables and shenanigans.
That Paxos simplified is as complicated as this.
It is simplified, obviously. So, right, like since then, there was a Cambrian explosion of algorithms that were improving both in terms of complexity and in terms of latency on these algorithms, and they keep going. So, for example, this is a really fun paper. Just say no to Paxos overhead. No stands for network ordering. This is by one of my colleagues from NUS, or Jelian, who is now at NUS. So that's just implementing some of the part of the Paxos in the network switches. Obviously, things are even more complicated, because not only the nodes might fail, some of them might misbehave. So what do we do then? So how can we possibly design a protocol that succeeds for the majority of honest participants who do not try to thwart the workings of the algorithm delivery. And you think it's unrealistic scenario, that actually it's very real. So it happens all the time in financial protocols and blockchains, and even in critical systems like in avionics. Typically, when we make the readings out of multiple sensors, some of them might malfunction, and that might affect the readings from the other sensors. And this is actually how this problem came to be studied. Lamport again. So he actually gave a very cute phrasing to this problem, calling it the Byzantine general program. So again, ancient Byzantine Empire. So several generals, each with their own army, are planning to attack a city, besieged city from different sides, but they don't have the direct sight of each other, so they communicate by messengers, trying to coordinate the attack or the retreat in the morning. So, and some of those generals happen to be traitors, so, and they send conflicting messages to different to other generals. So basically, how to engineer a protocol with enough redundancy so all the honest generals will still get the right decisions despite the attempts of the traitors. Funny enough, the Association of Computing Machinery now considers this title offensive because it offends old Byzantine Empire by associating with something bad. So I kid you not, this is actually in the guidelines. So they say like, don't use the word Byzantine, use adversarial. But the paper is still there and everyone still, uses it. Okay, so yeah. Practical Byzantine fault tolerance. Well, the name kind of stuck. So that's a famous paper again by Bardo Orliskov and Miguel Castro. This is actually the protocol which is very much used everywhere in production where they need Byzantine fault tolerance, and there are more effective versions. So something like hot stuff, and this basically keeps coming. And the main source of these protocols are kind of components of modern blockchain systems where they clearly like they try to optimize for latency, they try to optimize for specific scenarios and whatnot. So what I'm trying to say, this is a very active area. So lots of these distributed protocols are being developed, and many papers come out and many more implementations come out. Okay, so and naturally there are like issues there. So some protocols might be wrong, they might simply not deliver on these guarantees. So related to that, people in formal methods started to look at the verification of distributed protocol at least 21 years ago, probably more than that. That's one of the earliest references that I could find. So this is the proof in one of the competitors to Lean, Isabel Ho, still very much popular as a prover. And since then, things were coming. So for example, Ironfleet and Verdi, both are very influential papers. Ivy is a framework that just recently, last month, received the most influential paper award from 10 years at PLDI, and well, some of these frameworks by me and some others by other people, and they kind of keep coming because this is a genuinely difficult problem, how to build something that is A, general enough to capture all these flavors of distributed protocols, and B, is kind of useful, so something that people can use. And in terms of utility, I think all these efforts are absolutely not great. So they come out as, including mine. So they come out as a papers. They make a point that, well, they can verify something that the prior work couldn't do, and then they just die because no one in the industry actually wants to learn these new tools and no one wants to use them. So what do people use in industry for verifying distributed protocols? They use TLA plus. So TLA plus is actually, well, you guessed it, it's also something by Lamport. And funny enough that initially it has been designed as just logical formalism for paper, not even proofs, for paper specifications of distributed protocols and their properties. But Lamport at that time joined Microsoft, so he got a team, and that has been implemented first as a tool to validate the specifications just for basic properties. And then, crazy enough, it has been enhanced with what's called a model check-in framework, which you can think of a very, very rigorous testing. So TLA plus, so to speak, it's a framework to specify distributed algorithms, not the actual systems that we can deploy in production, but the designs, and then exhaustively test them. So it also has like some support for proofs. There is actually this thing called TLA proof system, labs. No one actually could use it in their right mind until recently, but nowadays LLMs, they just don't let certain things die because people now can use even tools that are unusable. The point is, TLA Plus is mostly used as a glorified testing framework, and it's immensely popular because it actually gives us really quick iteration loops. So, and on this time to benefit scale, so basically how much utility you get out of the tool for prototyping and verifying distributed systems, so TLA Plus scores really, really high because in just like if you have basic familiarity with a tool, and you need to have familiarity with the tool even in the age of LLM because you need to be able to read the definition of your system and the properties. So it usually takes like between 1 and 2 days to translate something even manually from a paper or just like from your head and design and write the basic property and then run this exhaustive testing framework up to like on certain finite instance of the system. So it doesn't give you the guarantee that the system will always work correctly for any execution length for any number of nodes. It basically says the system will work correctly for 5 nodes that execute up to 10 steps. So something like that. But there is a general belief if you execute for sufficiently many nodes to sufficiently many steps, going through this exponentially large state space, so people usually run it overnight, then, and you check that your property of interest holds, then your system is like with 99.9% guarantees bugged for it. Occasionally not, and there's a list of bugs that actually have been missed. But again, this thing has just tremendous utility, and that's what everyone knows it, and everyone uses it, and it's being taught in the classes. And Amazon, Microsoft, and Google, they all like use it in production for prototyping. Okay. Okay, what can you do that is sort of more rigorous? Well, the tool Ivy that has been mentioned actually falls into this land of automated verifiers. So it takes the distributed protocol model, it takes the properties, and it compiles them in a way very similar to what we have seen yesterday with the weakest precondition calculus into a bunch of verification conditions that are then sent to SMT. And that occasion, and this is actually like still pretty easy to prototype. The problem is that it actually kind of doesn't work most of the time because the verification conditions that you typically get out of properties and specifications of distributed systems, they are very large and SMT just like cannot handle them. So if you want to have a predictable yes/no answer from the SMT, you need to be very careful how you even write the definitions of using distributed systems. There is at least a couple of PhD dissertations, some of them lots of award-winning papers that just explain how you need to define your distributed system in the language of Ivy so your SMT would behave predictably. Okay, so if you kind of don't care about the predictability and you also want to scale it to something that is easier to extract to executable code and run, well, there is this framework called Ironfleet, which is built on top of Daphne. It's like one of the famous systems that everyone in the field knows of and everyone cites and no one actually ran because it's very much derelict. And that was a massive effort by like 10 people from Microsoft who have spent a couple of years basically building this framework for verifying distributed systems on top of Daphne, and they yield the real thing. It was not deployed in production, but it was still impressive. So, okay, I put weeks here, but and for the first time, it actually took much longer. The problem with Ironfleet is that since it's Daphne-based, there are certain properties that are still out of reach because Daphne is based on the first-order logic, not higher-order logic, like tools such as Coq and Lean. And also, oftentimes, you increase your trusted code base by adding certain axioms that you simply cannot prove in Daphne. So obviously, at the far end of the spectrum, we have efforts that verify systems in ROC. So I cite Growth. It's a paper from MIT. Again, this is not practical tool. It's perfectly fine if you have never heard of it, which I think is the case. But again, that's a paper that came out at a very prestigious conference, making the point that yes, you can write realistic distributed systems in ROC and you can verify it, and that took like many person years. So none of that, except for TLA, is practical. But even further, that if you actually willing to invest your time to do something like this, and then move something somewhere here to get stronger guarantees, and then eventually move somewhere here because now AI makes it simpler. There is no single tool that does that. So sort of like you commit to a particular tool, you commit to a particular language design, and you sort of stuck with it. And this is obviously like very good for making research careers because you can take TLA Plus and start building plugins for it, or you can take an Ivy and you can start building interactive proof mode for it, and you can do other things. And this was sort of the point that we were at 3 years ago with George and my other students. We were very aware of all this works in the space, and we thought, okay, this is clearly suboptimal. How can we kind of get all of that so we can have it in the single ecosystem and eventually get here? But like for anyone who actually wants to get some quick gains, they could start from here. And this is where like this idea of multimodality came in. So we implemented that in a single tool. If you want to verify distributed system in the full generality, but also start quickly, you either use a combination of tools or you kind of start modding your favorite tool so it would look more and more like an interactive theorem prover. So Ivy has a proof mode. TLA has a proof mode. They're all absolutely unusable. They don't have anything resembling Mathlete, but they sort of give you this escape hatch that allows you to write the proof when the command methods not work. So this is a joke, which is we call Perle's law. So Perle is my PhD student. And you know that this is rephrasing a famous law about any program that's sufficiently complicated contains a half of interpreter of Lisp. So this is our version. Every verifier expands until it contains an ad hoc, bug-ridden, and usable implementation of a half of interactive theorem prover. Those verifiers which cannot so expand are replaced by ones which can. Okay, so let's put an end to that. And actually, if you're interested in a more like technical perspective of why we have this opinion out of our very real experience, so there is this workshop paper called Lessons from Building an Auto-Active Verifier in Lean, which we published earlier this year. It's not a very formal paper. It's you can think of it a blog post in the form of a paper, but it documents all the design choices. Okay, so Veil. So that was our solution, and the solution was very simple. So we just built the whole thing in Lean. So instead of starting from SMT or from the testing tool and adding proof mode, we just started from something that gives us ultimate capabilities. As we have seen yesterday, if you're in Lean and you are very careful about your embedding, you can test, you can use SMT, and you can do interactive proofs. And obviously, this is all we got in Veil. Okay, so I'm going to skip through a bunch of slides which I inserted without, because I thought that I will give this talk first. I was not sure what kind of audience we are going to be here, but obviously I don't need to sell you Lean. So I don't need to tell you who Terence Tao is and why he's using Lean, because yeah, of course he is. Why wouldn't he? One thing that I'm going to mention is that speaking of the tools that have been built not by mathematicians for mathematicians in Lean, but actually by computer scientists, engineers, or like other people. So Cedar is one of the celebrated efforts that Amazon has in other realms, so it's authentication. And kind of a little bit annoyingly, they have implemented the whole framework in Lean. It works, it's verified, but they ended up not deploying it. Even though, like, why? And okay, you might think, okay, maybe performance was not good, but they actually had Rust implementation next to it, and the performance of Rust implementation was worse. So, okay, and then I just asked Byron Cook, who is this president of Amazon, they are like, why didn't you do that? Like, well, you know, anyone can maintain a Rust code base. So if we suddenly lose like a bunch of critical people who like can really hack like meta programming and Lean, we'll be dead in the water. So this is just for this purpose. So we
had said you need 24 hours support and we don't have enough Lean engineers for 24 hours.
That's exactly what he said. Yeah. Yeah, that's exactly what he said. Yeah. All right. So the future of a refined distributed protocol, as we want to see it, is like having this curve. So you have quick wins, and then eventually you have your hard-earned benefit if you're willing to invest more time. And maybe the curve is not even that flat because nowadays we have LLMs, and that was drawn before we had them. Okay. So what is Veil? So Veil is actually conceptually much simpler thing than Velvet we have seen today, because it works with one of the most basic mathematical abstractions that computer science has. And this abstraction is state transition systems. So, okay, some people define state transition system as a triple, but like I think we all have an idea that this is a formal model that says that has two components. So it has states, think of them like as pretty much anything, can be integers, can be records, can be arrays, can be tuples of all these things, can be even something potentially infinite. So, and it has transitions between the states, and it also, and the transitions meaning that this is the relation which says which state can transition to which other state. So if this is a relation is functional, then it's a deterministic state transition system. Otherwise, if it's a relation properly, then it's non-deterministic. So with this, we can model all the variety of state transition systems. And turns out that if you really zoom out from all the intricacies of distributed systems that they have, like the nodes and the node pass messages, they are just state transition systems, where the state is holistically the state of all nodes combined, plus all the messages that are currently in flight. So you can make something more bespoke, but this is effectively the model in which TLA Plus and other similar tools represent distributed systems. So if you want to model the messages, you just introduce something like a set or like array component into your state, and you record all the messages that you have sent. So it's very bespoke. So when we talk about transition systems, we are interested in multiple properties. Many of them are based on the idea of reachability, which is the transitive closure of the transition relations with regard to the initial state. Yeah, so the reason I said it's a triple, because typically there's also a third component, which is a designated subset of all the states, all the possible states, which are considered to be initial states. So this is where we start. So when we take the properties, we say that it's an invariant, which means that all the states that are reachable under transitive closure of the transitions from the initial ones, so that's what we call the invariant. So, and the inductive invariant, it's a slightly stronger notion, which is something that not necessarily you want, but very frequently you have to deal with it. It's very related to loop invariance that we have seen yesterday. So inductive invariant is an invariant that is closed under the transition relation. And again, so here, that's like, I'm going to come back to this point, but inductive invariants, they're just everywhere in computer science. And the reason is that computer science is, in a nutshell, proving properties of state machines. So programs are state machines, distributed systems are state machine, everything is a state machine in computer science. If we want to show that something holds for everything that is reachable, well, mathematical induction is your friend, right? So proof for zero, initial state, proof for any state that it holds, it also holds for all the next states. And the second property is exactly the inductivity of the invariant. Yes?
Assume that there's a sequentialization of operations in states. So that only are able to get this.
We are assuming what again?
Sequentialization.
I don't know what it is.
Some sort of linearization of the operations.
I don't think.
Happened in
I don't.
So this has nothing to do with distributed systems. And this is completely general.
This is mathematics. Yeah.
This is just
So,
completely.
yeah. So, but I'm not sure I understand the question. So can you explain?
my question is like, if you can, is it that we're trying to say that a distributed system can be modeled as a transition system, or
Yes, that's exactly what I'm saying.
okay, so I was just wondering how you can have only one sequence of operations.
Different state depending on.
No, I'm not saying that. So distributed system is an infinite tree or graph, and if you're willing to conflate identical states of something that are forest, if you start from a bunch of initial states, and then you iterate your transition relation, exploring through the infinity where it can lead you. So that is the semantics of a distributed system or state transition system.
But the difference between the last two is unreachable states.
Yes. So in that
state is reachable, then these two are the same.
Yeah. So inductive invariant. So remember we were talking about the least fixed points of the functional. So like, yeah, so inductive invariant is an over approximation of the safety property.
Why
Yes.
loops
Yeah.
invariant as against
Exactly. So I will have a nice picture to show that, but basically, again, I think for the room where like most of the people, to some extent, mathematicians, just thinking proofs by induction, that's a useful one, right? So your inductive hypothesis doesn't have to coincide with the property that you are trying to prove, right? So it needs to imply that the property you're trying to prove. Okay, so when we talk about distributed systems, so this is something which is slightly more specialized, but these are again very basic taxonomy of the property.
You mean reserved by every transition and also holds for initial states or just
Yeah. Preserve, yeah, holds for initial. Yes.
Okay, so the
Yeah.
difference is that it's an over approximation.
Yeah, it's an over approximation. Yes, thank you. Yeah, that was slightly inaccurate of me. Okay, so safety alignments. So this is actually the favorite example of the state machine, of the state transition system, over which you care both about safety and liveness, is an elevator. So safety means nothing bad will happen. In the context of elevator, it means it will not crash to the shaft, and it will not stop between the floors, opening the doors. Well, yeah, this is just like literally unsafe, right? So bad for everyone. So these are the bad states, and we don't want our state machine, like an elevator, end up with. Liveness is somewhat more subtle. Liveness says that good things will eventually happen. Because you can see, you can have a perfectly safe elevator that never stops on any floor. You press the button and you wait forever. I mean, this is safe, right? So, or you enter the elevator and it never lets you, like it goes up and down. I think we all had this nightmare. So good things should eventually happen, and this is the liveness property. And the liveness property is something that is surprisingly much easier to prove for sequential code, because you just need to identify loops as a source of termination and show that like you have the decreasing argument that makes them terminate. In the case of concurrent distributed systems, liveness becomes very subtle because you have these multiple parties that can interact with each other in a subtle way, and basically things just can be going in the loops, but in a very implicit way. So you will not have like an explicit loop that's you can see that node terminates. You have like one node sending the message, triggering another one, and yada, yada, yada. And then it goes the full circle. And furthermore, since there's a lot of non-determinism involved, because those systems depend on system schedulers, they depend on the latency of the networks, some of these scenarios might be unlikely, and you will have very hard time detecting them via conventional testing. So, and actually, again, aliveness is something that cannot be reliably, it can be obviously like empirically shown, but not cannot be reliably shown to be violated using testing, just by the nature of it. So aliveness is something that only is violated by infinite executions. But test by the nature is something that you can run only finite amount of time, right? So, and if it just didn't terminate, or maybe you just didn't wait long enough. So this is the problem with the liveness. So safety bugs can be reliably discovered with explicit testing or explicit state model checking. Liveness requires slightly more subtle approach, which kind of analyzes your system as a whole and detects potential loops in the execution. So, okay. So state machine. Yep.
Finite state models I agree will never prove liveness. But can it be proved if you have linear models or something like that? I mean,
So you see, even finite state models can have finite number of states, but they can have infinitely long executions. So they can agree. It's
your notion of models where you can try to prove liveness.
I'm not,
Maybe I'm not taught you. So
Yeah.
I'll ask later.
Yeah. Right. Now, the problem with this is that there are so many angles at which people come to reason about distributed systems. Some people like are shown LTO first and they think in these terms, and some people, I'm very kind of pedestrian in my understanding of how things are. So state transition systems, the most basic thing.
Right.
So let's,
I guess my analogy is that, for instance, we do prove termination at times and can say termination is roughly like liveness. So, but that's a
Yeah.
true conceptual
Yes,
not
yeah.
model. Yeah.
Yeah.
Okay.
Okay, so yeah, we are just going to model like from the first principle distributed protocols as transition systems. We are going to explicitly say that each state has multiple nodes and each transition is atomically performed by one node. That means that like parts of the transitions cannot happen, it just happens as a whole. And effectively, you are at the liberty to choose what exactly is your unit of atomicity. Is it sending one message? Is it broadcasting message? So actually all these choices, they have names. So they are usually referred to as asynchronous system or synchronous systems. And synchronous system is informally the one that bundles multiple physically different events together. So which is far less realistic, but still very useful if you want to focus on particular aspects. So nodes communicate by sending and receiving messages, but that's not necessarily how we are going to model that. Okay, so the Hello World program, Hello World protocol in distributed computing is electing a unique leader between a bunch of nodes that are connected in a ring topology, by which I mean no single nodes know of all other nodes. Each node only know who is its next neighbor. And all the nodes, they also carry some unique IDs that are totally ordered. You can think of them as integers, not necessarily from the same segment. There might be gaps, as long as, but there is a total order, and it will be clear why we need one. Okay, so how, have a question? Or no, okay, how does the protocol work? So it's actually, again, it's that simple. It's not fault tolerant. It actually doesn't tolerate even a single node crashing, but let's stick with it anyways. So the goal is that these nodes need to uniformly agree who is the leader, meaning that only like once the leader like is elected, this node should know that it's a leader, and no other node should think that they are a leader. What are they doing with this leadership status? We don't care. So that's probably part of some other protocol. We just want to end in the state when the leader is elected, and we want to make sure that there is no such state when there is more than one leader is elected. The protocol is actually that simple. So since each node only knows its successor in this ring topology, it just sends its own ID to this next node. So here's 1, sending its own ID 1, to its successor, which is 5, and other nodes, for some reason this doesn't work reliably for me, so okay, and other nodes, they do the same thing. Okay, so I'm showing one possible execution. It doesn't have to be this way because concurrently with some nodes still sending the messages, other nodes might start receiving the messages. And when the node receives a message, this is how it reacts to it. It compares the sender ID with its own ID. And if its own ID is smaller than the sender's ID, it relays this message to its successor. If, however, it receives the message from someone with a smaller ID, so the node itself is larger, it just mutes this message. So example, so here we have Message from 1 to 5 just gets muted by 5 because 1 is smaller than 5. So the same happens. So here, the message from 3 to 1 gets relayed by 1 to 5 because 3 is larger than 1. And the same things can happen to other messages. 2 to 4 just disappears. This one gets relayed. This one gets relayed, and etc. And you see where we are going with that. So any idea? How do you think we are going to elect the leader? So it knows that it's a leader.
The message comes back to yourself.
The message comes back to yourself. So you see, if the message made the full round, it really came through all the nodes and no one has muted it. So it's from the largest node, and the largest node is automatically the leader. But the whole point of distributed protocols is that no one has this holistic view. We live in the world, and this is kind of an accurate model in the sense that no one has the full information about the world, except for the God, maybe. And that since we're like no one hears the God, so they need to communicate with each other. So like they would all agree who is the leader by passing this message. Okay, so eventually 5 gets this full round, and it declares itself as a leader. So importantly, no other nodes declares itself as a leader. And this is exactly the property that we want to establish. That the safety property that there is at most one leader. So meaning that if 2 or more leaders, that never happens. Bad things never happen. So, and this is a safety property, and this is actually something that we can test for, but we can also verify for by induction on the length of the execution protocol by showing that this property holds the initial state, and then it's preserved by the transition. Although it's not that simple. So we are going to see. So let's see how can we move from this design to the implementation. I'm going to show you Whale, and this is something that you can look at in this dedicated view. Although we don't have a very beefy virtual machine at NUS running it, and my internet connection is also not that good. So yeah, I'm gonna play it safe and show it locally. Okay, so here we have, see, it's a Lean file. And what you're looking at is another shallowly embedded domain-specific language in Lean, and this is the language of Whale. So we define immutable scalar values as you can think of as parameters of the protocol. So all nodes are just the list of their identifiers. And there is a function, total one, that says how we map the node to its next one. So at this point, these things are abstract deliberately because we want to be able to reason about this protocol or prove it for all possible configurations of node and all possible such functions. And we also want to run it for different collections of nodes and different topologies. So that's why these things are left abstract. And then just for to make it more fun, we presume that there might be multiple leaders. So the leader, and this is actually something that is mutable, as opposed to this, is represented by a list of identities. Finally, we declare the structure which will serve as a message. So there is a payload, which is the ID of the node, which there is a source, which is actually the same as payload, and there is a destination. None of that is enforced through any property or defended times of this structure. This is just something that will happen intrinsically in the protocol. Oh yeah, and we also have this field called individual. Why exactly individual? That's for historical reasons. We probably should also add another keyword field for that. This is effectively all the messages that are currently in flight. This, after init, defines the set of the initial states. So in fact, Whale gives you this convenient notation where this is a relation, but this is a relation that also can be thought of as a piece of imperative code that produces this. So it's just, no one says that this necessarily needs to be a deterministic program. It actually can produce different outcomes. So it just happens that this one is deterministic. How exactly we produce non-deterministic programs? You remember from the lecture yesterday, we have this indifferent phase operator. So we can have that too. So at the end of it, we have the initial state. In this case, it's unique. So we have like no messages and no one is a leader. Okay, so how do we model what's happening in the protocol? Okay, so we have an action send, which, again, there are probably 10 bazillion ways to model protocol, which randomly picks a node from all the nodes and performs this action implemented by this procedure, which this node sends the message to the next one. So it forms this message by just creating this data structure. And if no such message has been set yet, it just appends this message to the list of existing ones. Again, this is that simple. And the reason why I'm saying that there are multiple ways to implement is that effectively what you see here is the same syntax as Velvet. So anything that you can write as a program in Velvet, you can write as a definition of an action in Whale. it might as well be just pure Lean. So this is kind of the nice thing, that if you want to write your definitions with these actions as vanilla Lean, you can have it. Receive. Non-deterministically pick a message that is currently in flight, check what's the destination, remove it from the messages currently in flight, and this is the important part. If we got the message from ourselves, so the payload is the same as we are the destination, and we are not yet a leader, make ourselves a leader by appending us to the list of the leaders. Otherwise, if the message actually is from someone with a larger node ID, relate to the next one. Otherwise, the message is already consumed, so it's as good as muted. Okay, so
The last one is shared mutable state, or is it part of the rest?
leaders part of share. So a leader is again. So you see, this is in just this implementation. So again, this is very bespoke implementation of ring leader election. So if you want to attach the leadership bit as a piece of state individual for each node, you can do that. It just will make the encoding slightly more complicated. It will not change the kind of the.
But here it's shared.
It's shared mutable state. No, I mean, this is kind of the thing which people find like very natural, but once you realize that you actually don't lose in generality or adequacy by just modeling your like individual distributed systems as merged representations of this state, then well, life becomes much easier this way. So some systems like such as P by Ankush Desai from like Amazon, they actually like give you more kind of realistic-ish look and feel by having like send and receive as primitives and giving you like different assertion language, but this is just more general. This is like as mathematical as it gets. Okay, so here is the safety property. So the safety property is that we have no more than one leader. So far, so good. The point is that let us not even try to prove this property. Let's check this property. So I'm going to do that by this model check command. And this is where interesting things happen. Because remember, we didn't say what are the concrete nodes and what is the concrete topology. So here we are going to do that by specifically instantiating these nodes to 1, 2, 3, 4, 5, and us instantiating the topology as this total function. With these concrete things, magical things happen. Veil actually generates an executable implementation of this system, which if you think of it is not entirely trivial because it actually needs support all these things. And it runs exhaustive enumeration of all possible executions. So it actually finds as many states like this, that many of them are distinct, and the longest execution is 32 steps. So if we increase, I mean, obviously this is grows as fast as exponents. So probably we want to go something, we want to show something like this because otherwise it wouldn't be a ring topology. Yeah. But the problem with larger states is that they tend to take very, very long. So you see now it keeps going and it keeps counting. The funny thing that we are doing that for the very large models, we are also simultaneous. So this actually is interpreted. So that's why you can see how it's going. So yeah, but we also in parallel compile it. So for the very long running models, the compiler in Lean is unfortunately somewhat slow. So, but once we get the compiled one, it runs like 2 or 3 orders of magnitude faster than the interpreted one. So if you actually got a model that is like quite large and you want to run it overnight, you will get more benefit from the compiled one. The interesting thing is that this is a model checker which is actually formally verified. What does it mean to formally verify a model checker? So that means that the definition of the system symbolically tells you which states are legal under symbolic interpretation of the relation. Concrete model checker says, okay, so these states are, this is the states that we are going to explore with this concrete instance. So what you want to show at the soundness is that there will be no spurious states which are not captured by your symbolic interpretation of the system that appear in the concrete model. This is actually very important because these systems might be, these states might be such that the system reports a bug on. Oh, by the way, let's have a bug. So haven't seen the most interesting parts. Let's violate something. Okay, let's like kind of like remove this condition. Okay, so when we go back here, and this runs the model checker, and let's see. Okay, so it finds the violation quite quickly. So this is actually the exactly look and feel that you get from TLA Plus. So TLA Plus is very effective. TLA Plus comes with TLC, very effective model checker, which when it finds the violation of the property, not it just says that the property has been violated, it gives you the exact trace from the initial state going through the sequence of transitions with very concrete arguments of what has happened to the state that violated the property. And here indeed we see we got the two leaders. So you see, this fast feedback is actually absolutely crucial, because if you're kind of wipe prototyping your distributed protocol, you're just experimenting, you really don't want the prover to be your correctness oracle. You want to iterate quickly, you want to have tests. So, and this is actually something that concrete state model check-in gives you. By the way, this is Lean widgets. So wonderful plugin for Lean that allows you to display arbitrary parts of your proof state and your file in the info view. So one of my students, George, he also has like a very fun plugin, which is not this branch, which kind of tries to understand what exactly your protocol is about. Then it asks an LLM for rendering of domain-specific representation of the state, and instead of seeing something like boring like this, you will see the pictures of like in this case I think like the king that is being elected. So instead of having two, you will have like two kings sitting in the list. So I think there's like a big potential of good UI design and human computer interaction, LLM powered with this domain specific formalism. Okay, so this is not verification, but this is Lean and this is multimodality that's Spinus. So we have just found bug in the protocol design by exhaustive test. And when, by the way, you talk to people who say that they have verified things in TLA+, that's what they did. So they ran this thing overnight on a sufficiently large instance of the parameters. And if they've got no bugs, that's as good. But obviously there is no 4.0 quantifier there. So this is effectively testing. So these papers that you have cited, that's what they did, right? Exactly. Okay. So surprisingly, this is not what we implemented first. This has been implemented maybe 2 years into existence of Whale, because initially Whale has been built as a verifier, and we realized that verifier for systems that like you cannot run is absolutely useless for the users, because no one is actually going to bother to verify it. Okay, so let's actually before we talk about the verification component of Whale, yeah, any questions about what happened?
Compiled version of the Whale now. When compiling, one can have concurrency.
It can, yeah.
Is it multi-threaded?
It is multi-threaded.
Okay.
Yes, it is. It is multi-threaded. It's actually the crazy thing that this is about on the protocols that matter, like Paxos, Raft, and everything that people actually consider important. It's like about 5 times faster than TLC. So we wrote a paper about that, how to certify a model checker and have it faster than TLC. It got rejected because people said, like, why do we need another model checker? TLC works just fine. So that's anyways. So intermezzo. Who has seen Die Hard 3 movie? Wow, that's more than usual. Do you know what I'm gonna show? No? Okay. This is a movie which is probably older than most of the people in the room. It's an action movie with Bruce Willis. Actually, not the best one. So the first 2 Die Hards are much better. If you have a chance, please watch them, especially on Christmas Eve. They're very good. So the third one is kind of okay. It has Samuel Jackson, and it actually has this episode. So assuming the sound works, let's just like, I don't know, like spend 2 minutes like watching something fun.
At a bar, you know, let's go ahead and grab it. Well, you're the cop. And Simon said you're supposed to be helping with this. I'm helping. But when are you going to start helping? After you get the bomb. Be careful. Don't open it. What? I got to open it. And it's going to be all right. Shit. I told you not to open it. The message. It's out of proximity circuit, so please don't run. Yeah, I got it. We're not going to run. How you turn this thing off? On the fountain, there should be 2 jugs. You see them? A 5-gallon and a 3-gallon. Fill one of the jugs with exactly 4 gallons of water and place it on the scale, and the timer will stop. Must be precise. 1 ounce or more or less will result in donation. If you're still alive in 5 minutes, we'll speak. Wait a sec. I don't get it. You get it? No. Get the jugs. Obviously, we can't fill the 3-gallon jug with 4 gallons of water, right? Obviously. All right, I know. There we go. We fill the 3-gallon jug exactly to the top, right? Okay, now we pour that 3 gallons into the 5-gallon jug, giving us exactly 3 gallons in the 5-gallon jug, right? Right. Okay. Then what? Now, take the 3-gallon jug, fill that a third of the way up. He said be precise. Exactly 4 gallons. Shit. I got less than a minute. Throw this thing away. Look, we can't take it off and it'll detonate. Just wait a second. I got it. Exactly 2 gallons in here, right? Right. Leaving exactly 1 gallon of empty space, right? Yeah. A full 5 gallons here, right? Right. You pour 1 gallon out of 5 gallons into there, we have exactly 4 gallons in there. Throw it in there. Come on. Come on. Don't spill it. Good. Was that 4 gallons? You're good, McLean. Put it on the back. Get it down there. Shit.
What does it have to do with model checking, you might ask? Can someone suggest how can we solve it using model checking? Okay, I'll give you a hint. So pouring water between the 2 jugs of 5 and 3 gallons is actually a state machine, right? So every single state can be described. Sorry?
Also filling to the capacity with each of the gallons.
Well, that's the thing. So there's more than one solution, but we only need one. So this is the system. Initially, so we have just 2 variables. Initially, both have 0 gallons of water, and we model everything that can be done. This is how we get fill the small jug, fill the big jug. So, and you see that means that the other means empty small, empty big, small to big. So this is where it gets slightly more complicated because we need to account for the difference that remains and that big to small. Okay, the only thing that we know of how to state safety property and use exhaustive exploration to find violations. How do we disarm the bomb? How should we trick the system into giving us the solution? We need to find a state in which the big jug has 4 gallons without solving the problem, just making the model checker do it for us. Okay, remember, safety property is something that states that bad things should not happen. So let's revert the bad and the good thing, right? Let's make, yeah. So try to prove that this never happens. So obviously this is luckily for us, luckily for the characters in the movie, this is not the case. So we're gonna run the model checker and it's gonna tell you, oh, look, we have found the violation of the safety property. And look, I'm gonna tell you exactly how it's violated. So these are the things that you need to go do to come to the state when the big jug has exactly 4 gallons. This is a solution. It's not the only solution, but we don't care. So this is actually really, once people realize that you can rig your exhaustive state space exploration into solving puzzle like this, they start having lots of fun. So the other exercise I typically give in the class that I'm teaching, this one is this one that I think we have in all the cultures, that we have the wolf, the goat, and the cabbage, and we need to move them across the river. So yeah, it's exactly the same thing. So it basically allows, you can specify how you can move with the farmer and the wolf, and who ends where, and your constraint is that everyone is on the far of the river. And yeah, so this is kind of the solution as you see it, and hopefully our visualization also highlights the things that are changed. I think it's quite fun, isn't it?